In this video, we will make a detailed derivation of the weak form for linear elasticity, such that this one can then be used in finite element programs like FEniCS. Let's get started. Hi and welcome to this new video. You might have already watched the last video where we coded a FEniCS solver for the clamped cantilever beam that you can see up here. The weak formulation was kind of coming out of the blue there, and it was necessary in order to convey the physics in form of the partial differential equation, or in its weak form, to FEniCS. This weak form builds the basis for the finite element method, and FEniCS can use it in order to assemble the stiffness matrices and then solve it in order to get our numerical solution. In this video, I want to go over the process to go from the strong to the weak form in really great detail. But before that, I just want to quickly recap on the cantilever beam, such that we can build up the boundary value problem, which underpins the physics, and then we will make all the transformations step by step. So let's start by creating a quick schematic for this clamped cantilever beam. So this was a three-dimensional problem, so we were looking at this three-dimensional domain here. And the idea of the beam was that the entire left face is clamped, so this face is clamped, and clamped means that our primary unknown, the displacement vector, will be 0. So our cantilever beam is not allowed to displace on this left face. And that's also what you see here in this rendering, that the left end is not changed in comparison to the reference configuration. On the other 5 faces, so this face, the face in the rear, the face here, this one, the bottom one, those are so-called free faces. So these are free faces, and that means we have no traction here. And we will soon see that in the boundary value problem, that this one is a homogeneous Dirichlet boundary condition, and this one is a homogeneous Neumann boundary condition. And then this cantilever beam was under its own weight, so it is under own weight, and this weight, or the corresponding force, is deflecting the beam. So we will have a gravity G, which acts as a body force. So let's use this information in order to assemble the boundary value problem. And this one consists of, well, most importantly, of course, our partial differential equation. And here, this is an elliptic PDE of the form that the negative divergence of the Cauchy stress tensor is equal to the body force. And here, this is a more generic body force, F, which could potentially consist of multiple components. But in our simple scenario, this will just be the gravity vector. And this holds for all positions in our domain omega, and in essence the cantilever beam, that's the domain. So everything in here, that is omega. Now we have a PDE for sigma, which is the Cauchy stress tensor, but the primary unknown in linear elasticity is the displacement vector. So actually there is no u in our PDE, right? And that's where the other two sub-equations came in that you might have seen in the previous video as well, which are needed in order to go from u to sigma. So first we have a constitutive law, and there we get that the sigma matrix is equal to a lambda times the trace of the epsilon matrix times the identity tensor of the 3x3, so in 3 dimensions, the 3x3 identity tensor, plus 2 times mu times the epsilon tensor. And these are the constitutive laws for linear elasticity. But hey, there is still no u inside, because we have another equation which relates the displacements to the strains, and here we use engineering strains epsilon, and those are given as a symmetric part of the displacement gradient. So 1/2 of gradient on u plus gradient on u transpose. And now there we have it. So we have a relation from sigma all the way to u. And if we were to plug in the chain, so plug in the sigma into the divergence and then the epsilon into the sigma expression, you would see that we have 2 differential operators applying to u. So here we have the gradient, and then we would get a divergence, and this will turn our PDE into a second order problem because we have exactly two spatial derivatives on our primary unknown u. By the way, of course, there is no time derivative here because we're looking at the stationary problem, which also turns our PDE into an elliptic problem. And of course, then we also have to define our boundary conditions. So we have u is 0 on the left face, so on left face, and that would be this one here. And then we have our Neumann boundary conditions with the no traction on all the other faces. And if you've done any PDE problems before, then Neumann boundary condition always looks like, well, we take the derivative of the primary unknown with respect to the outward facing unit normal or in that particular direction and set it to 0. But in the problems of linear elasticity, we prescribe the traction vector, which is given by the multiplication of the sigma matrix with the outward forcing unit normal. So this might seem a little bit odd for a Neumann boundary condition at first, but it will make sense in a second. So we will have sigma multiplied with n, which is the outward facing unit normal vector, is equal to 0. And this is on all other faces of our domain or our cantilever beam. And the reason this is a Neumann boundary condition is that if we just use the sigma matrix, we have exactly one derivative in it. And that's basically also the property of the Neumann boundary condition, that we are not prescribing the actual primary unknown on the boundary, but we are prescribing its first derivative. And with the unit normal vector, we are also letting it point into the right direction here. Well, then let's use the boundary value problem in order to derive the weak form. So the next step will be to derive the weak form. And the first step in our derivation is to multiply with test function. So we're going to multiply the PDE, so the main part of our boundary value problem, with a test function. And this test function will be a vector valued function, which is of the same type as the primary unknown. So it will be a 3D vector function. So this is a 3D vector function, or let's call it maybe a vector field, such that it is similar to the displacement field, which was the primary unknown, which is the vector u. So don't confuse that u with v here. Well, then let's take our equation. So we have minus divergence of our sigma tensor. And then this expression has to be multiplied with v. And I want to have a contraction here. So these weak forms are always scalar contractions. And if we take the divergence of a matrix field, we get a vector field. So that one is given us an three-dimensional object. And if you want to contract that down into a scalar, we would have to take the scalar product with the test function v. So we do the transpose v. You could have also just put a dot in here, but I want to separate the divergence operator a little bit from the linear algebra operators. So I will use this transpose structure. And then by doing so, the resulting expression will be a scalar. So that's for the left-hand side. And for the right-hand side, let's look at it. So here we just have our body force F, and then we have F. And of course, here we also need the contraction down to scalar. So we have F transpose V. That is the first step. Let's go to the second, which is to integrate over the domain omega. And the domain, of course, that was our cantilever beam. And so we get an integral over omega. And the left-hand side will be negative divergence of our sigma tensor. And then this one transpose multiplied with the test function v, and then integrate it over the volume. So I will use dv, and don't confuse that here. This is a capital V, this is a volume integral. So in 3 dimension, this will be a triple integral. And of course, this is something different than the test function v. The right-hand side will also be an integration over omega with f transpose v, and then integrate it over the volume. And if we now look at the weak form where we want to arrive at, we already have, one element here. This other looks a little bit strange. So let's go on to the third step, which is an integration by parts. So integration by parts. But the question is, why should we want to integrate by parts? And that is because our PDE problem is of second order. And that was because we have one differential operator here and another differential operator on the displacement strain relationship. And by the integration by parts, we want to turn this into a first order problem where we will then only have one spatial derivative left on the primary unknown. So in other words, since here we only see one spatial derivative because the other one is hiding within the definition of sigma, we want to somehow move the nabla operator to our test function. So maybe let me informally rephrase that such that we get turn the divergence of the sigma tensor transpose V into something like, well, we want to have the sigma and then maybe some multiplication with an derivative operator on V. So this is really informally. How can we turn this more formal? And there are now two approaches. I first want to use a symbolic notation and then also an index notation to make that fully clear what is going on here. And the idea is to use a reverse product rule. So we will do a reverse product rule. You will see this in a second. This is a typical trick in those derivations. And for this, we will take the divergence of a hypothetical quantity. So let's imagine we would have a quantity which is the matrix product of the sigma tensor with our test function V. And of course, if we have a matrix multiplied with a vector, that would be a 3D quantity. And if we were to take the divergence of that, this would turn it into scalar. So just to have that down here, this one is a 3x3 matrix. Then if we multiply a 3x3 matrix with a 3-dimensional vector, we get a 3-dimensional vector. And if we take the divergence of a 3-dimensional vector, we get a scalar. Now we want to apply the product rule to that expression, because then we could potentially find this expression again. So well, let's do that. I mean, it's of course a little bit weird to have product rules in these higher dimensional objects, but it will make sense. So first let's take the divergence of the sigma tensor. So divergence of sigma tensor. And if we take the divergence, so maybe let me put that here. So this is again 3x3. And if we take the divergence of a matrix, we will get a vector. And now in order to still get our contraction down to scalar, we have to scalar multiply that with the test function. So then we will get our scalar value again. But now we have to also apply the divergence to the V test function. So we will get sigma matrix multiplied with the divergence of V. Okay, well, let's play around. So this one was a 3D vector. And if we take the divergence of it, we will get a scalar. And then here we have our 3x3 matrix. That does not work. So the 3x3 matrix multiplied with a scalar will give us a 3x3 matrix. So the equation would not be fulfilled. So, but we have to think of it a little bit loosely here if we want to keep the symbolic notation. So in other words, we only want a derivative operator on V, not necessarily the divergence. I mean, we could also take the gradient, for instance. So let me delete that. And instead of the divergence, use the gradient. So if we have a vector field, which is of dimension 3, and then we take the gradient of it, we get a 3x3 matrix, a matrix field. And if we then take the inner product for matrices, which is the double contraction denoted by the colon here, we again get a scalar value. So once again, we use an expanding operation with the gradient on a vector field, get a matrix field, and then make an inner product between two matrix fields in order to get a scalar. And if this looks a little bit fishy to you, since we did some kind of an engineering here, let's do the same thing in index notation. So I will change back to the blue color. And for this, let us write the matrix vector product of sigma with V in index notation. So we will have sigma ij multiplied with Vj, and then we have to take the derivative of this one with respect to xi. So we get an Einstein summation convention by the matrix vector product summation over j, and then also with summation over I by the indices, and then here we would also have a contraction down to scalar. Then this one would be, so in index notation it's rather straightforward, so we will first get the derivative on sigma, which would be derivative of sigma ij with respect to xi multiplied with vj plus sigma ij multiplied with the derivative of vj with respect to xi. And here you can see that this expression is a divergence because it is contracting. So in other words, we have the indices of the numerator in the derivative and the denominator appearing both in this fraction, whereas here we have the gradient, or in other words, an expanding operation where we have two different indices. And then if we have the Einstein summation convention here, we would have a summation over both I and j, which gives us the double contraction. Technically, we would get the double contraction with sigma transpose, but since sigma is symmetric, those are identical. So, I mean, this would be a little more technicality, but since sigma is a simpler tensor, we can use it that way. I hope that made sense so far, but now the question is still there, why did we do the reverse product rule? And the idea is that here an expression arises that we already know, and then we can rearrange for it. And then we get the following expression such that the divergence of the sigma tensor transpose multiplied with the test function v is given as the divergence of sigma multiplied with v minus sigma double contracted with the gradient of the test function. And if we replace this expression in our integration, then we are one step closer towards our weak function. So back into the integral, so let me note that down, back into integral. We then get on the left-hand side of the equation our integration over omega with first this expression. And we have to be a little bit careful because there was a negative sign here, which we did not consider in our derivation. So let me add that one here. So we had a negative sign, which gives us a negative sign here and a positive sign here. So then back in the integral, we here get minus divergence of sigma multiplied with test function v integrated over the volume plus integral over omega of sigma double contracted with the gradient of v integrated over the volume. And then on the right hand side, we have the integration over omega of f transpose v volume integral. I mean, this step was called integration by parts, but so far we haven't done any integration by parts because technically, if you look at it here, we still have an operation where there is a spatial derivative on sigma. I mean, in the second part here, we already moved it over to the test function v, but here there is still one. But luckily, there is the Gauss or divergence theorem, which we can apply here. So let's use the Gaussian or the divergence theorem, which states that if we have an volume integral or domain integral over the divergence of a vector field that is equal to the product of the outward facing unit normal vector multiplied with the expression we were taking the divergence of integrated over the surface. So this one is identical to the integral over the surface. So the omega of the expression, which is sigma multiplied with test function v, and then scalar product with the outward facing unit normal vector n integrated over the surface. And then of course we keep our negative sign a minus here. And this now helped us with this theorem to also avoid the spatial derivative again. And now we only have one spatial derivative on our primary unknown u. As said, it's a little bit hidden because the sigma already contains one by the constitutive laws and by this displacement strain relationship, but at least we now have a preliminary weak form, which I want to note down. So we have a preliminary weak form, which then is, and I want to have it in a form that I use this one on the left hand side and move all the two others to the right hand side. So we have the integration over omega of sigma double contracted with the gradient on the test function integrated over the volume is equal to the integration over the domain of f scalar product with the test function integrated over the volume plus integration over omega of sigma times the test function scalar product with the unit normal vector integrated over the surface. And just to refresh that, since sigma times v gives us a vector, this is a valid inner product for a vector. And why did I call it preliminary? Well, if you now look at where we want to arrive at, in the beginning of the video I noted that down, there it still looks a little bit different. So here we have an epsilon on v, on the test function. What does that mean? And on the right hand side we have t transpose. What is t? So technically this is what you could already use within FEniCS, but we want to make that more concise or bring it into a form that is more commonly used in linear elasticity. But before we can go there, I noted a mistake, so this should be d omega to get the surface integral correctly. Well, then let's note down the two parts we want to change. So we have this one over here, I want to call 1, and then we have this other one, which we will look afterwards. So let's first make some changes here. For this, I will write that expression down once again. So we have the sigma matrix vector multiplied with the test function, and then transpose with the unit normal vector. Let's make some linear algebra modifications. So let's apply the transpose to that equation, which reverses the order and applies the transpose to both parts, which gives us v transpose sigma transpose n. And then we know that sigma is symmetric, so this is equivalent to v transpose sigma times n. And then we know that sigma times n is exactly the traction vector. So this one is defined as the traction vector, which is the way we would prescribe Neumann boundary conditions. So we would get v transpose t. And of course, this is just made for generality. Here in the scenario of the clamped cantilever beam, the other phases where there are Neumann boundary condition, there is no traction, and no traction means that the traction vector is 0. And this is then almost what we have here. So if we go back down again, so I will just note that down, that in our scenario this one is 0. So here t is 0, but I want to keep it for generality, for instance, if you have a surface force. And then we can also know that this is just a scalar product, and there the order does not matter. So we could either have v transpose t, or we could equivalently have t transpose v. And this now turns this surface integral into the form we have seen it in the intro. Lastly, we have to look at point 2, which will be a bit more complicated. For this, let us look at the gradient of the test function. So the gradient of the test function will of course be a 3-by-3-dimensional matrix field, since v is a 3-dimensional vector field and we have an expanding operation. And now I want to do an additive decomposition of that matrix into a so-called symmetric and anti-symmetric part. So we say that the gradient of v is going to be the symmetric part of the gradient of v plus the anti-symmetric part of the gradient of v. I think it makes sense if we extract a symmetric part and an anti-symmetric part, add those two up, we arrive again at the original expression. Since this is a little bit abstract, I want to look at it with an example. So let's, for instance, take a matrix A. Here it's just a matrix with arbitrary values inside. So this matrix has the following structure. It has 8, 7, and 3 on the main diagonal, and it has like 2, 1, 2 here, and then it has 3, 2, 2 here. And you can clearly see that this matrix is not symmetric. So it has, well, in these two entries it would be symmetric, but in the other off-diagonal entries it is not. If we compute the symmetric part of this matrix A, we would get the following. So we of course keep the main diagonal of 8, 7, 3, and then have here 2.5, 1.5, 2, and then of course here a 2.5, a 1.5, and a 2. And I computed the symmetric part by using the 1/2 of A plus A transpose. And then we can also compute the anti-symmetric part. So the anti-symmetric part of our matrix A will then be 0 minus 0.5 minus 0.5, 0.5, and 0.5. And then 0, 0, 0 here. And we compute an anti-symmetric part by just taking the original matrix and subtracting the symmetric part. So this one is A minus the symmetric part of A. Why did I do that? Because now we can go one step further and look at the contraction that we do here with sigma and the gradient of v. So let's go into the next step and continue with our original integral. So where we had that sigma is double contracted with the gradient of v. Well, this is then just nothing else than sigma double contracted with the symmetric part of the gradient of v plus sigma double contracted with the anti-symmetric part of the gradient of v. And now we will use a property from linear algebra that the contraction of a symmetric matrix with an anti-symmetric matrix, or it's also sometimes called skew symmetric, is going to be 0. So this one will always be 0. Okay, let me give an example to you. So let's, for instance, take a sigma matrix which has the following entries. So it will be 5, 1, 2, 1, 3, 1, and then 2, 1, 2, because sigma matrices, these matrices are always symmetric, so I chose an arbitrarily symmetric matrix here. And if we then again use our anti-symmetric part here, for instance, say let's double contract this Cauchy stress tensor with the anti-symmetric part of this arbitrary matrix A. This will then of course be element-wise multiplication. So we have 5 times 0, which gives us 0. 1 times minus 0.5 gives us minus 0.5. 2 times minus 0.5 gives us minus 1. Then 1 times 0.5 gives us 0.5. And 2 times 0.5 gives us 1. And the rest, of course, will be 0. And then if we add up all the components, we get 0. And I mean, it's just an example, but this generalizes. So the idea is that the product of a skew symmetric or anti-symmetric, so skew symmetric and a symmetric matrix will always be 0. And as a consequence, we know that the inner product of the Cauchy stress tensor with the gradient on our test function will essentially just be the Cauchy stress tensor double contracted with the symmetric part of it. And if we then look at the original boundary value problem again, we see that there is an operation which produces the symmetric gradient, and that's essentially the displacement strain relationship. So we can kind of misuse it for our test function as well. So finally, we could also say that this one is equal to the Cauchy stress tensor double contracted with the epsilon engineering strain on the test function. And in order to make that clear where the quantities come from, we say that the sigma based on the actual displacement double contracted with the epsilon based on the test displacement. And then we have our final weak form, and that's essentially the one that you have also seen in the intro. So we will have the integral over omega of our domain of the Cauchy stress tensor based on the actual displacement double contracted with the engineering strain of the test displacement integrated over the volume is equal to the omega integral of the body force, in our example the gravity, scalar product with the test function integrated over the volume, plus a surface integral of the traction vector scalar product with the test function integrated over the surface. And in our case of the cantilever beam, that would be 0, since the traction vector is 0 on all the 5 Neumann faces. But that's the final weak form. That works for linear elasticity, and you can also use it on different cases than just the cantilever beam, because you could also prescribe Neumann boundary conditions, and this allows us to solve simple structural mechanics problems in FEniCS. You can download the PDF of the handwritten notes with a link in the video description. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. If you enjoyed this video, then please consider liking and subscribing. There are more FEniCS videos and finite element videos on this channel. I think you will enjoy them. Here you will now see similar videos, and I hope to see you in one of the next videos.